Let's look at number 3. They give us this table with some information about 4 compounds. Tells us the boiling points, the bond lengths, and the bond strengths of each of them. And then they want us to explain a lot of these physical properties. So explain the difference in the properties given in the table above for each of the following pairs. So let's look at 1. The bond strengths of N2 and O2. Well, let's see. N2 is right here, and its bond strength is 226. And O2 is right there, and its bond strength is 118. So clearly nitrogen has a stronger bond strength than oxygen. How are we going to explain that? Well, it's pretty easy if we draw the Lewis structures, so let's draw the Lewis structures. So in A, part 1, we're going to do nitrogen. And nitrogen, there's no central atom because there's only 2 of them. And if we're going to count how many valence electrons to use to draw the Lewis structure, it's 1, 2, 3, 4, 5, and there's 2 of them, so that's a total of 10 electrons to work with. I'm going to work on the outside first. We're going to go 2 there, 2 there, and 2 there. I'm just choosing that atom as the outside. You've noticed we've used 2, 4, 6, 8 already, and then 9, 10, so we're done. And we can't stop there because the nitrogen on this side is not happy. It only has 2, 4 electrons, so we got to share. So I'm going to erase these. If I can still erase them, sometimes I can't. If I do something else, I can't erase them. So what we're going to do is we're going to erase these like that and drop them down. And then we got to do it again because the nitrogen still only has 6 electrons. So I'm going to erase these and drop it down. And so what we end up with is a nitrogen-nitrogen triple bond. And that's probably going to be the reason why it had more strength. If we do the same thing with oxygen, oxygen connected to oxygen, we have a total of 1, 2, 3, 4, 5, 6. There's 2 of them. 6 times 2 is 12. So we have 12 to work with. We go like this, connect it, and then start working on the outside. We've used 2, 4, 6, 8, 9, 10, 11, 12. But the oxygen on the right isn't happy, so we're going to have to go backwards and erase these 2 and drop them down. And then it looks like everybody's happy. We end up with 2, 4, 6, 8 electrons on that oxygen, and 2, 4, 6, 8. So oxygen has a double bond, and I think that's the reason why nitrogen has stronger bond strength. So let's write our argument. It feels like we should say more than that, but I think this is enough. N2 contains a stronger triple bond compared to the double bond in O2. We identified that the nitrogen was stronger based on the data, and we explained why. It has to do with the type of bond. I think we're done. Let's look at A, part 2, the bond length of hydrogen and chlorine. Let's see which one's longer. Well, hydrogen has a bond length of 0.75, and chlorine has a bond length of 1.99. It's clearly a lot longer. This one's, I think, a pretty relatively simple one. If we were to draw a diagram of hydrogen, hydrogen's up here, and it's one of the smaller elements on the periodic table. It has 2 1s orbitals that are overlapping, kind of like that, and they're really tiny atoms, whereas chlorine, and you actually can't see it the way I've got the periodic table right at the moment. Let's see if we can slide it over a little bit. Chlorine is right here. It's in the 3rd row, so it's quite a bit further out. We're talking about p orbitals, and they're going to be a whole bunch bigger. So, we could draw p orbitals if we wanted to, sort of like that, but they're going to be huge. And I think that's going to have to do with, a lot to do with the answer, is the distance between the 2 chlorine atoms is going to be a lot greater than the distance between the 2 hydrogen atoms because the orbitals that are overlapping are bigger. Alright, so let's read what I came up with. The valence electrons in chlorine are in a higher energy 3p orbitals that are significantly larger than the 1s orbitals involved in H2 bonding. This results in the Cl-Cl bond being longer than the HH bond. So what could you have gotten away with not saying? I mean, could you have gotten away with not identifying the orbitals at all? According to the Princeton Review Guide, their opinion is, yes, you could have just simply said that chlorine atoms are larger, and therefore the bond distance between them will be greater. Hydrogen atoms are smaller, and the bond distance between them will be smaller. So, it all kind of depends on the grading that day on AP, but certainly if you know something about the orbitals, it helps quite a bit. All right. Alright, now we're down to A, part 3. Now you notice what I like about this question is it's been fairly unpredictable. For the first one, you needed to draw the Lewis structures to figure out the bonds that were in it to determine bond strength. The second one had to do with orbital overlap. This third one, probably of all of them, is the most predictable. Whenever we're talking about boiling points, we must be talking about intermolecular forces when we're talking about covalently bonded compounds. So this one, much more straightforward. All we got to do is go through, identify the intermolecular forces in each one of these, and then say why one would be stronger than the other. Alright, so let's see what we've got here. Remember, I'm going to mention the type of intermolecular force in each one of these first. So the intermolecular force between oxygen molecules is London dispersion forces. Remember that we got to use this word between. If they don't feel like you clearly understand that this is not a bond inside the oxygen, they're unlikely to give you credit for it. So make sure that we're talking about the force between oxygen molecules. I've identified or labeled what my acronyms mean now so I can use them. The intermolecular force between chlorine molecules is London dispersion forces also. Then I come to my conclusion, which is going to be based on the data up here. The boiling point of oxygen clearly is much lower. It's negative 182 than chlorine. That's a much higher one. Remember, we're talking negative numbers, so negative 34 is a much higher boiling point than chlorine. And the reason is because chlorine must have stronger intermolecular forces. So our conclusion is going to be based on that idea. So the London dispersion forces between chlorine molecules are stronger, that's an important statement, than those between oxygen molecules. We knew that just simply from the data, resulting in chlorine having a higher boiling point. Then we get to the reason why. This is because chlorine has more polarizable electrons than oxygen. Remember, polarizable electrons is the key to determining which molecule will have more London dispersion forces. This is a go-to word. It works great. Alright, and finally we're down to 3b here. Use the principles of molecular bonding to explain why hydrogen and oxygen are gases at room temperature while water is not. So we've abandoned the table. We don't need that anymore. And this is a pretty easy one because it's just like the boiling point. Whenever we're talking about phases, of course water is a liquid at room temperature. The reason is because it does hydrogen bonding, whereas these two, all they have is London dispersion forces. So it's a good old-fashioned intermolecular forces argument, and let's see what we can come up with. So we're going to identify the type of intermolecular force in all three compounds, then we're going to sum it up. So the strongest intermolecular force between hydrogen or oxygen molecules is LDF. Remember that I predefined this in parts A and we're still in the same question, so I think I can get away with that abbreviation. You notice I was a little bit careful. I was worried about, I don't want them to think that the intermolecular forces between these two compounds, that's why I put the word or instead of and, because I didn't want them to think between hydrogen and oxygen. We know it's two hydrogen molecules and two oxygen molecules that we're talking about here. I don't think they'd be that nitpicky, but it does worry me a little bit. Then we got to talk about water. The strongest intermolecular force between water molecules is hydrogen bonding. Notice we're using between for each one of these. It's really important that we clarify that we understand intermolecular force is not a bond inside the water molecule. And then lastly we conclude. Hydrogen bonding is a stronger intermolecular force than London dispersion forces. I actually wish I had said hydrogen bonding is typically a stronger intermolecular force than London dispersion forces, because we know that that's just a trend. Anyway, it results in water being a liquid at STP, acceptable abbreviation, while hydrogen and oxygen are not. So I think that should do it.